we're given this problem. A curve is given by the following expression right here. It says if y of -3 is equal to 2, evaluate dy over dx. I'm going to assume that it just means evaluate dy over dx, the derivative of y with respect to x at this given point, -3, 2. This -3 is the x value, the input, and this 2 is like the output, the y value. So the first thing to understand is that this thing right here, this monster, is something called an implicitly defined expression. And that kind of just means there isn't like a y in terms of a function of x, or there isn't like one variable in terms of one other. So to get a derivative of this, you're going to need to use something called implicit differentiation. And that's going to be this thing right here on the bottom. You're just going to essentially apply the derivative to the whole thing. And since we're asked to find dy, derivative of y with respect to x, we will do the derivative with respect to x right here. So you can tackle this thing just thinking of it as like the normal derivative. So x to the fifth, that's going to become 5x to the fourth by using power rule. And this next part is where it gets interesting, because these two things right here, those are two things multiplied into each other. And when you're doing the derivative, you might want to think of product rule. We need to use a product rule for this. And so let's just go ahead and briefly talk about the product rule, and I'll also talk about what this means here on the bottom. So let's say we have two things multiplied into each other, like two functions, f of x and g of x. The way that I like to personally think of the product rule, I like to think of it as, the two pairs, except one or the other is the derivative. This is f prime times g plus f times g prime. Now, you might find that it may look a little bit different when you look it up or you see it on your textbook, and that's okay. That's because, the way that things are multiplied to each other, like 1 times 2 or 2 times 1, they're the same thing, or how adding things in different orders, it doesn't matter. But, for right now, we're just going to go ahead with this. And so now I'm going to show you what this is right here. This right here is the result of using the product rule. So let me explain what happened. This is x to the fourth. I decided to do the derivative of it, and that means it gets left the same. Now let's do the other combination, add it. X to the fourth stays the same, and y to the fourth is what we're taking the derivative of. And so this is where it gets a little bit interesting. So first thing, just think of it like the normal derivative, just do power rule. And this right here is what's new. Now, this happens because we are differentiating the variable y when we are actually differentiating everything with respect to x. They do not align. We're not differentiating x. This is y. So what happens is we need to put dy, the variable that we're doing it to, and then with respect to x. If you want to think of it as a shortcut way, just think every time you differentiate something in terms of y, just multiply that afterwards. And now we're going to do the same thing for y to the fifth. It just becomes 5y to the fourth. Think of it normally, and then just, this is implicit differentiation. And we're doing it with y, but with respect to x, so we just need to add that. And then that number just dies off. Derivative of a constant is 0. And so now, what's going to happen here is we need to isolate dy over dx algebraically. So let me briefly summarize this chunk that I'm going to show you right now. I'm going to move this over since it has nothing to do with dy over dx. And at the same time, I'm going to distribute this inside to both of those. And this is what it looks like, the next step. So you see the negative, it's here. And then I also put the negative right here. And you'll see that I just have the 4 moved in front instead. That's the only thing that's different. And now the next step, what I'm going to do is these two right here. These are common terms in the sense that they're multiplied by dy dx. So we're going to combine them, and then at the same time, that has nothing to do with dy dx, so I'll move it over. That next step is going to look something like this. And so, sorry about that. So now that we have that, we can divide all of this to finally isolate dy over dx. and we will have this. You can go ahead and pause to check the work and see. I'm just trying to get through this as quick as I can briefly. So this is essentially our expression for dy over dx. You can plug in an x and y coordinate and it will tell you the slope at that point. Of course, it has to be a point that really exists on this expression. So let me now go to Desmos since I have it set up. So this is what I have. I have a representing x, b representing y, plugged in -3, 2, and this is the value that I get. And that is how you're going to use implicit differentiation to evaluate a derivative at a particular point. And you see -3, 2 really does exist here. And I also went a little extra here. I did, since slope of the tangent line tends to be related to sometimes those kind of problems, I did that, and you can see that it pretty much follows it right on it. So I hope this was helpful and that hopefully you start to you get a clear idea of how you do this and what methods to take, what approach to take.